Hello, my name is Raúl and I'm going to talk to you about our work that we are carrying here in central Argentina. I want to start by talking about the idea of mountain systems as ecology labs. We know that mountain systems have a specific climatic pattern and they determine they shape the alpine life in general. For example, the tree line. And we also know that mountains are not perfectly homogeneous, so um, microsites are very relevant to plant life and alpine life in general as well. They can explain enemies patterns and other patterns of uh, biological populations. Highly interesting. And a good example, this is an example that we saw in a previous work, actually carried out by the team of Rodriguez in the 2017. They found that lichens tend to respond strongly to elevation. They form specific communities in the mountain tops, in the middle elevations, and there are cosmopolitan communities as well. They also respond strongly to microsite. There are specific communities in the north-facing rocks, in the south-facing rocks, and in the rocks without slope. So, community patterns are not the only way to see these responses. We can also measure some things like physiological or morphological changes, which we call it to that traits. And we know that lichens are poikilohydric beings, meaning that the water content is regulated passively. They respond strongly to the environment. They depend on the environment actually. As we are seeing here in the video, lichens respond it's very strong to the environment. So I let the link there if you want to check the whole video. So we can measure some of these features. We can measure the amount of water that lichens retain per area unit. This is water holding capacity, and we know that hydrophobicity of lichens changes depending of the according to the thickness of the layers, for example, or other anatomical features. I'm not going to detail now. So we use some species. These are our aimed species, Parmotremas, with several morphological modifications along the gradient in Usnea amblioclada. So we measure this in the elevational gradient. We measure water holding capacity, and we measure the hydrophobicity by measuring the time that water droplets were absorbed by the thallus. This is an idea that I took from Daniel Stanton. He gave me the idea. He's working with it in his lab, and he gave me this method so I can do it in my work also. So our results is that hydrophobicity in Parmotrema decreases along elevation and decreases at south-facing rocks. And we also found that water holding capacity in Parmotrema is the opposite, increasing with elevation. And at microsat level, we actually don't see a clear pattern. And I'm going to talk to you about this later. Hydrophobicity of Usnea amblioclada decreases with elevation and increase in south-facing rocks, which is a more logic pattern because south-facing microsites are more humid, so increasing hydrophobicity can be a strategy to avoid early saturation. Okay, so this is the same pattern. Basically, hydrophobicity increasing over time in south-facing rocks. Sorry. Okay. So in a climate change scenario, the patterns that we are seeing in the lowest elevations will happen in the highest elevations. So these are the patterns that are interesting for us. We see that Parmotrema change hydrophobicity but in the middle elevations, while Usnea amblyoclada change its hydrophobicity features in the microsites but in the lowest elevations. A similar thing happens here with water holding capacity. The Parmotrema doesn't change so much in the microsites in different elevations, while Usnea amblyoclada do change a lot of water holding capacity in the microsites at a lot of elevations, we could say. So our final considerations is that these traits respond to the environment, they respond to elevation and microsites, as we hypothesized before. Sorry, because I didn't pronounce that well. And our conclusions is also that Usnea amblyoclada physiological responses are stronger at lowest microsites and lowest elevations, meaning that in a climate change scenario they will have a wider range of action. So this can be an advantage for the species. While Parmotrema species doesn't change at microsite level so much. So in a climate change scenario, even if they have a little range of action to migrate to cooler microsites, we hypothesize that Parmotrema will tend to disappear. So I want to finish by giving thanks to the organizations because of the grant that allows me to present this work. I want to thank to the Argentinian CONICET that gave me the grant so I can work my PhD, to my workplaces, the CERNAR and the INVIP, and to my team, my advisors and the volunteers that helped me a lot during the work field. So thank you so much. Thanks.